Energy Management Plan. Establish an energy management plan. To establish an energy management plan, we need to follow these 6 steps. We have to organize the effort. We may need to do a little bit of research to get started. We cannot just start turning valves or turning switches. We have to have a plan. Sure, we can turn the air off. We do not have to be a rocket scientist to say that will save energy. Okay, we can turn the power off, but that does not make any sense. Let us do the things that make sense and have a plan. Determining our historical energy consumption is the first step. What are we using right now? There are so many small system operators that do not have a clue as to what they are paying or using on a monthly basis. As part of our historical energy consumption, we are also going to track our specific plant data. For step 2, we suggest that we get at least a couple of years of historical information together. Past electric bills so we can see what we have done in the past and what we are doing now. Not so much necessarily from a cost total consumption, but from a kilowatt hour consumed perspective. Costs are changing. We get new negotiated contracts. Last year, in our small Maryland system, we were paying 8 cents per kilowatt hour. This year, we are paying 6 cents per kilowatt hour, and other charges in the tariff may also have changed. We still want to look at those items, but we have to keep in mind that it may change from year to year. What we are really looking at is our kilowatt hour consumption. Step 3 involves performing an audit as part of our plan. We are already on a monthly basis or daily basis, already gathering data for our operating reports. So we are tracking some key items already. We need to decide from that list of data what do we want to use to match or compare with our energy consumption. We do not need all the operating data for our energy consumption comparisons, but we should look at our monthly report and say this would be important to have for consumption information. One example of what would be on our monthly operating report that is important for us is flow. Flow is probably the most fundamental piece of information. The reason flow is important is because that is the one thing that is changing, especially if we are a wastewater operator. Flow is up and down depending on the weather, time of day, and the seasons. For example, in Ocean City, Maryland, their flow changes significantly between winter and summer. We want to track flow as one example. Another example may be dissolved oxygen or DO. We may want to track the DO if DO is a problem for us. For instance, we are operating a plant and cannot get the dissolved oxygen down to the 2 mg per liter to 4 mg per liter range, or we find that we cannot ever get it below 4 mg per liter. We would want to track the dissolved oxygen level, because if lowering the dissolved oxygen is one of the changes we decide to make, we would need to track what impact it had on the process over a period of time. We know we can change the dissolved oxygen, but how well do we control it over a period of time? Step 4. Evaluate these measures and decide if they are cost effective or not. If they are, we should implement the measures. Step 5. We then continue with Step 6. Monitor our power consumption and savings. This is when we say we come up with all these measures we are going to do. It doesn't end there. We have to track it over and over. The other reason we want to look at our plant data is to have a record of anything we may have done operationally that could have changed our process numbers or energy consumption. Establish an energy management plan. The first step in establishing an energy management plan is to start by establishing roles and responsibility of the team. Determine who should participate. Even as a small system operator, even if we are the only operator working for the utility, we are still part of a larger team. There has to be someone in control of the budget. there has to be someone who pays the electric bill. Find that financial person who can approve the team to spend the money to do what we say we're going to do as part of our ECM. We may even need an engineer to consider energy conservation for future projects. Teams can vary. If we are a larger facility, we may have electricians on staff, whereas the average small system uses an electrician from the local town. Team members do not need to be staff members. We can include the electrician from the local town. So, if we have an electrician, we want him on the team. If we have mechanics, we want them on the team. Why? Because they all play a role in what's going on. For example, let's say we have a strategy where we do not run two XYZ pumps at the same time. All we need is one mechanic to make a mistake and run two pumps during a maintenance check, and there goes our ECM savings. Working in a team changes the way we have to handle things. We must have procedures established that state clearly, unless this is going on, this does not happen. We have to have everyone on the same page. If we have a big plant or multiple people involved, everyone needs to know what the strategies are and what we are trying to do. We have to get a copy of our power company tariff. We have to understand the tariff because we can look at desktop savings just by understanding the tariff. Sometimes tariffs have time of day rates. That is easy to evaluate using a desktop evaluation. Ask ourselves, is there anything we are doing in the plant where we can change the time of day it is done? We should really understand the tariff as it describes how we are being billed. The tariff has some technical language such as power factor, and that is language we may want to have clarified to understand better. In your team, established rules or boundaries. And of course, set goals. As a team, we may decide to work on 2 energy-saving measures this year, or we may decide to only look at 1 energy-saving measure for the year. We may decide, if this works, we can save enough money so we can buy this item and move to the next energy-saving measure we have on our list. Organize the conservation effort. Planning. Operations. The operator says my first priority is to meet the permit, so whatever we are establishing cannot interfere with that. Unfortunately, most of the plants that are ENR have yearly total loadings, and we do not really know if we are in violation until the last month of the year. We may need to establish standard operation procedures or SOPs and guidelines. Operators need to understand that if they shut a chemical feed off to save energy, they are going to cause us to violate phosphorus limits. Or if we turn a second pump on, whenever we have one pump already running, we are going to pay an additional X number of dollars in demand charges. We have to establish procedures and ensure that everybody knows what they are, and also have a good justification for them. Maintenance, generally speaking, needs to be proactive, such as cleaning diffusers. If we are in an ENR system, we probably have fine bubble diffusers. One of the things they can do is clog. Or if they are the membrane type, then they start to open up and we get big bubbles versus little bubbles. So it does help to have a proactive maintenance schedule. We may need to bump our diffusers every so often to slough the material off of them. We need to be proactive. For example, changing air filters when they are supposed to be changed and not delaying. Studies have concluded that we can save up to 5% in energy costs strictly by having an active preventative maintenance program. If we have electricians and mechanics, they all have a role to play. Electricians are routinely in the panel, so they can start tightening connections when there. Believe it or not, that can save energy. We can measure amperage on the 3 legs to see if they are balanced. What test instruments do they need to have? If we have electricians, they should probably have a watt meter and a power factor meter because they are authorized to use them. This means we must be aware of their SOPs as well as ours. Management may have to spend money to save money. If we run the calculations and provide supporting documentation, then we can show management what we believe we are going to save. This is not an exact science, but if we can show them that when we change this item, it could slightly change something else which works to our advantage. We can provide supporting calculations which show our conservation methods payback. Management then needs to decide how these savings are to be used. One suggestion is to roll the savings into the next energy conservation measure, or put it towards operator incentives. We suggest incentives or rewards because management may be surprised the kind of things that operators can think of to save money if they knew there was an incentive for them. Give them some reason to pay attention to this plan. The team may even want to develop a replacement and upgrade policy. Decide right from the start, what are we going to do when one of these old motors fail? Have the calculations done for that. We may even want to consider financing a go green option. We have to decide if we are better off spending our money on this ECM, or would it be better establishing a CD? Are we going to make more money that way? Let the financial experts on our team make those decisions. Obtain the power company tariff. It is important to get the power company rate structure for our facility. The power company provides a tariff that has multiple rate structures in it. We should focus on the one that applies to us. This will help us zero in on how we are charged. Once we see what our rate structure looks like, we will begin to understand how we are being charged for electricity. We need to understand the terminology. Sometimes it can be fairly complicated. What types of information might we see? You can see an example of a tariff in your course handouts on page 1 and 2. There is going to be a minimum monthly charge. It may be called standard service. This is the basic amount we will pay for having electric service. We are going to pay this fee regardless of what we do. We will also see an energy charge. This is the cost per kilowatt hour. Generally speaking, we are going to be paying 10 cents per kilowatt hour or less in most of the Maryland for this fee. There is going to be an energy demand rate. We may see billing seasons or times. Some utilities could have winter and summer rates, which others may not. Generally speaking, energy consumption will be the highest in the winter for most utilities. Most of us have higher electrical usage in the winter because we have heat running to keep chemicals and buildings from freezing. We will also see a distribution service charge. This fee is for the utility to take care of the lines and the cost of delivering the electricity to the plants. We may see a power factor charge. Most of the tariffs have a power factor in their rate structure, so they can charge us for a poor power factor. We may have regulatory changes, and those are also something we cannot do anything about. We may see a power cost adjustment and incentive options. One incentive used by one utility in Southern Maryland is to request that they shed load by using their plant's standby power. If they can switch over to standby power within 5 minutes of receiving notification and maintain it for the duration of the request, they receive a significant payback for that month. The only thing they have to worry about is having someone there to start the generator, or having a system that will allow them to start the generator remotely. Nowadays, with PLCs and SCADA, this can be done remotely. We have to understand the tariff language. We call it an incentive, but they may use different terms or descriptions in the tariff. There are many possible rate structures, so be aware of the terminology. Let's review the handout Schedule GSD General Service Demand. This is an example of a tariff from a utility in Southern Maryland. Again, this will be on page 1 and 2 of your class handouts. We can see that this schedule is for a user with a peak demand that exceeds 25 kilowatts. So if we have a business treatment plant, pump station, or other system that is going to use more than 25 kilowatts, we are going to fall under this rate structure. Remember that 25 kilowatts is approximately 25 horsepower. We are using math here where 1 horsepower equals 0.746 kilowatts. So roughly speaking, a 25 horsepower motor is going to be using about 25 kilowatts. The structure describes the type of service as single and three-phase. Next, we see the rates. It has the winter and summer rates. It just so happens on this schedule they are the same at $5.89 kilowatt demand and about 5 cents per kilowatt hour for energy consumption for both winter and summer. We also have distribution charges. Again, what is it telling us? It is all kilowatts. This is not a tiered system. Some systems have a tiered system where customers pay so much for the first thousands of kilowatts, then after that pay so much for the next group of kilowatts. This tariff does not have a tiered structure. If the utility has a tiered structure, the thing to remember if we are shaving off energy charges is we are actually shaving them off at the top end, not typically the more expensive rate. We are shaving charges off at the rate that is probably cheaper. With most utilities, their basic charge is going to be the higher charge. Then, when they go above a certain amount, it becomes less expensive. When we go to save, we are then saving at the cheaper rate in a tiered structure. So that is why it is important to look at our structure, because if we are going to calculate what we are saving and a payback period, we need to know at what kilowatt hours we are saving. Are we saving at a cheaper rate or do we have a flat rate? This bill is a flat rate consumption, so anything we save is at the 5 cents per kilowatt hour. Also notice with this tariff, there are flat rate facility charges that we cannot do anything about. It is the consumption numbers we can change. The next page is the facility's rate structure. This is an important item to understand. Sometimes it becomes fairly technical and we may need some help understanding it. Take a look at the determination of billing demand and read it. We read that the kilowatt demand is a 15-minute integrated demand. So for example, when we turn a pump on, let us say it's a 15 horsepower pump, then we are drawing approximately 15 kilowatts. Your electric meter that is reading that 15 kilowatts has a racketing feature. That means that if we left it on for 15 minutes, it locks at 15 kilowatts. If we shut it off somewhere in between, wherever the ratchet was, it's where it stops. But then the next time we start something that is over that value, it starts to ratchet again until we get to a locked point. After 15 minutes, it reaches some peaked value, and that is what we are billed for. We may have only done that one time a month, but we could be billed that way for a significant period of time. In this case, it was for 11 months. The point being, that is why SOPs are important. If we mess this up once, we are paying for it for 11 months. We have to try to stay with the procedure we established to control this. In this example, if we said this is our conservation measure and this is how we are going to reduce demand charge, and then we changed it, then we have messed ourselves up for 11 months. It takes 11 months to reset the demand charge. Understand that demand charge is one of the most significant things we will find in our rate structure, and it is usually based on a 15 or 30-minute integrated demand. All it means by integrated is it is a ratchet type of device. As it gets to the end of that demand, it locks into place and that is where it stays. Otherwise, it is continually moving up. Each month, the utility resets this reading and measures our peak demand over the next billing period. We can also see that this tariff has a power factor charge, saying that if we are less than 90% or 0.9, they can charge us. We really need to study our own tariff, but this is the exercise we should go through and do while reading our tariffs. Now let's review an invoice. You can find a SMETCO invoice in your course handouts on pages 3 and 4. This SMETCO invoice is for a small treatment plant. We can see that the first sheet says General Service Demand, winter. So it is a winter rate, and as we saw in our tariff earlier, the winter rate is the same as the summer rate. There is a meter reading, and they are telling us that the meter multiplier is 80. What they are telling us here is if we take a reading and multiply by 80, we will get the actual usage. The kilowatts hour, total energy usage, was 76,880, and the demand was 129.60 kilowatts. A rough ballpark we are dealing with here is somewhere around 100 to 125 horsepower worth of equipment that was running at the same time for the designated time to establish that demand. Remember, with this tariff, that was a 15-minute value, so that occurred for at least 15 minutes. As we move down the bill, there are standard office services, and we can see that this particular energy charge in this case on this bill was about 8 cents per kilowatt hour. There is a structure which allows for usage over 8,500 kilowatt hour at a different rate, and that is what they did in this case here. As we look at this bill, we can see that they had 68,380 kilowatt hours over the 8,500. So if we took the 76,880 total kilowatt hour minus the 8,500 kilowatt hour, that equals 68,380 kilowatt hour that they are charged 0.0671 cents per kilowatt hour. If we are working on kilowatt hour savings, at what rate are we saving? This is a significant part of what we need to be able to grasp and understand. Are we saving at 6 cents per kilowatt hour or 8 cents per kilowatt hour? We are saving at the 0.6 cents per kilowatt hour because no matter what we do at this point, we will never get below the 8,500 kilowatt hour minimum unless we start turning things off completely. So in this case, we are going to be saving roughly 0.67 cents per kilowatt hour. Why is that important? It doesn't sound like much, but we are trying to determine a payback period with 2 cents per kilowatt hour. If we think about how many hours there are in a year, the number gets real high, especially on something that is running all the time. Move down to some of the other items on this invoice. We can see that we have an energy demand. Our first 25 kilowatt hours are free. They are part of our service, but all kilowatts over 25, in this case there was 104.60 kilowatts, are billable. How did we get that? We took the 129.6 kilowatt measured demand minus the 25 kilowatt to equal 104.60 kilowatt at a cost of $6.37 per kilowatt. We can see that demand is a big part of this bill. Starting equipment up, that is a big charge, $6 versus 6 cents. Anything we can do to reduce kilowatt demand is going to result in significant savings. Then we have all of our other adjustments we talked about: the power factor, the cost adjustments, the distribution charges, bill stabilization adjustment, all kinds of other things that no matter what we can't reduce these basic charges. But they do add to the cost, and we can see that is less than pennies. How we decide to put that into our spreadsheet depends on how much it adds to our rate, but we do have to consider those numbers in our cost. On the right-hand side of the bill, it says the kilowatt demand for this period was 129.60, and that matches what we saw on our meter. The tariff. Most of this we have covered already. We want to look at the type of service we have, our minimum monthly charge, what our standard services are, the energy charge, energy demand, billing seasons or times, distribution service charges, if there is a power factor, regulatory charges, and power cost adjustments and incentives. Those are all things that we are going to want to try to get to the bottom of. We may have to ask specifically about what incentives they have for load shedding and so forth. Understanding the electric bill and rate structure. The basic energy charge is the cost of having an account. No matter what we do, this is what we are going to pay. Energy charge over a specific kilowatt hour. This is a charge where we can typically shave our cost. We cannot negotiate much here. Those negotiations are done through the agreements we have with our power utility at the beginning. After that fact, we cannot negotiate much there. On peak usage, we may have on-peak and off-peak rates. For example, 9 a.m. to 10 p.m. is what the power company in our example calls the on-peak time. Off-peak is 10 p.m. to 9 a.m. Again, look at our bill or our structure and it will tell us the on-peak and off-peak rates and times. Are there any operations that we can switch time of day? Backwashing filters is one we hear a lot. Obviously, that is one we can do to get some savings. If we are not a 24-hour per day operation, that may not be a real option. Another example may be our plant has a fine bubble diffuser in a basin and we need to change the airflow rate to about 2 CFM per diffuser to do a good bump of the diffuser to remove accumulated deposits. To do this, we have to more than double the airflow to the diffuser to clear it off. Can this be done off-peak? We can see where that could be a significant airflow issue and resulting energy cost. Can we run the generator once a week and do the air bump during the generator exercise? We could even exercise other equipment at this time to avoid the demand increase in cost. For on-peak and off-peak seasonal times of the year, we get different rates. Usually on-peak is higher. It may be one rate for the first 100 kilowatt hours and another for the remainder. We saw that on the one bill we reviewed, off-peak can be lower and covers the nighttime. That is usually when the off-peak is. We can save money by moving operations to the off-peak time. We have given several examples of measures we can do off-peak. Understanding the energy charge. Let's talk about electrical usage or energy consumption kilowatt hours. Usage is over a period of time. It is continuous and it is determined by how many kilowatts we are using over that specific period of time. We can see on this graph that it goes up and down throughout the day depending on what we are doing, such as starting and stopping equipment. Some equipment automatically starts and stops. Other equipment may speed up and slow down. Regardless, our system will have a similar pattern of peak and low energy consumption periods throughout the day. Understanding demand charge. Demand is a moving block of time. In this slide, we used a 15-minute period. Our demand meter is looking at and measuring instantaneous peak demands, and it gives us a measured peak demand based on that 15-minute window. Remember, it's like a ratchet device. When we start up equipment, the ratchet moves up. But when we stop that equipment, the ratchet doesn't go down. The ratchet stays at its measured peak demand. Is there anything that we can do to minimize this peak? We saw in that one tariff the demand cost was $6 per kilowatt. That is expensive. That is why it is very important to examine how and when we operate our equipment. One suggestion is to think about staggering equipment operations. It may be possible to save money here without the need to do a payback analysis. We have big energy users, and if we can stagger the starting of this equipment, we can save energy. We are not saying start this at this minute or start that one the next minute. That is not going to do anything for us. It has to be greater than our 15-minute period of time we're talking about here. Explanation of power factor. The power factor can be an extra charge or credit. There is usually a charge if we are less than 0.9 and a credit if we're greater than 0.9. Most motors require more power than what is actually required to operate them. That is what the power grid sees, so the electric utility says, well, we have to have that power capability there when they may need it. The ratio of what is used or consumed compared to what needs to be supplied is the power factor. Poor power factor can be corrected. To correct poor power factor, they make power factor correction capacitors that can be installed throughout the system. Now there is some debate about power factor correction capacitors actually saving money. So let's look at the math formula and see for ourselves. Go back to the formula for calculating kilowatts. If we increase the power factor in that formula, then we have to decrease the amperage by a greater amount to save energy. So if we are going to increase power factor 5%, then we are hoping our power factor correction device lowers the amperage more than 5%. If we lower the amperage more than 5% and we increase the power factor 5%, then our formula says we are going to save energy. We are not saying a power factor correction is always going to save us money. It depends, but it will lower your amperage draw, and this will allow your motor to run cooler. If the motor runs cooler, then it will last longer. Reducing power always saves money. If we can shift usage from on-peak to off-peak, that can save money, and controlling demand can save money. We may need to monitor our process control systems in real time. We are all dealing with new technologies today. We have these process control systems that are actually monitoring and managing power, and in some cases, even the small systems may have them. If we have a process control system, we probably have some kind of power monitoring system. This is a good way to look and see what we're doing. It is probably one of the pop-up screens at our workstations that we never open. If we went to it and started a particular piece of equipment, we would see on that screen what that equipment did to energy consumption. So as a desktop check, we should look at the power monitor graphics. Establish an energy management plan. When we are talking about this planning stage, we want to make sure we establish rules and boundaries, assign responsibilities, involve others on the staff, and make one change at a time. We already know that works from the process work that we do. Make one change at a time and wait and see how that works out. Again, this is a small system approach, and we are doing everything from a notepad and calculator. We know on paper our ECM said it would save money. We do not want to do too many things at the same time because we want to be able to assess the measures we took. Does it really make a difference? Set goals, find our resources, and look at what will or can we invest in. This is the key. There are all kinds of new devices now that we could install at our plant, such as ammonia analyzers and nitrate analyzers, but they cost a large amount of money. Do we have the money to invest in that, and what can we possibly save? We have to do a rough calculation of what we could possibly save, and will it pay for itself? If it will not pay for itself, there may be no reason to have it from an energy conservation perspective. Somehow, we have to decide what is the useful life for a piece of equipment. We can count on motors lasting for 20 years. That is what we do here with this whole process. What are we going to say is a reasonable period of time? Usually, if we can say we save money in 5 years or less on just about anything, with the exception of ammonia and nitrate analyzers. We should ask at the plant or talk to some experts about how long does that type of probe last. We know plants that have probes, and some have replaced them 1 or 2 times a year. It is hard to believe that can be paying for themselves under that scenario. There is not an endless life to these devices, so we need to somehow determine the useful life for that measure we came up with. Again, if it is an ammonia or nitrate analyzer, what is its useful life? The other thing to consider are the costs associated with having that measure implemented. Do we have to pay an electrician or a mechanic? Do we have to modify something? What is the cost of labor to implement this conservation measure? We need to keep in mind that a lot of these considerations, suggested at times, do not include labor costs. So if we use our staff, then that labor is cheap. But if we do not have these labor experts on staff, and we have to bring somebody in, then all of a sudden we may have doubled the cost and payback period. The labor may be the most expensive part of what we are trying to do, so we have to somehow establish a useful life for the measure we are looking to do. We could say most of those probes, at least from what we are hearing people say, do not last more than a couple of years. One thing or another causes them to fail, whether it is an electrical issue, bad signals, or just the atmosphere they have to be in. DO probes are one of the instruments we must have available to have a chance at reducing or controlling our airflow. We also need to consider the maintenance measures that are required for these devices. Because this maintenance may make them more accurate, or it may make them last longer. We may need to evaluate the cost of doing field or lab analysis. Some of the rules we establish at the beginning may include: are we going to include labor as part of our assessment? Or are we going to say no? This is a good conservation measure and we want to do it because we are focusing on good measures. Establish a baseline. To establish a baseline, we will need to determine our historical consumption. We should compile past data and suggest looking at the past 12 to 24 months. We want to do this for the same period with our operating data also. We don't need all of our operating information, just the key information or parameters that are related to our processes. Flow being one big number we are going to want to monitor. Ammonia levels, nitrate levels, and DO levels are other things we are going to want to at least consider. Summarize each process kilowatt hour and inventory the equipment needed.